My goal in this discussion is to leverage the insights you have in diffraction and the point spread function to understand how to practically take advantage of this as one does optical imaging. So resolution, of course, is the question of how much one can resolve detail in an image. And it relates basically to the grain of the image. We've talked about this in previous discussions. If we take a pair of points of objects, resolution could be asked, how close could those points get and you would still have confidence in saying that they're two separate points and not one? And you can think about this in many ways, but you can see that there's no absolute way, no absolute criterion that would allow you to say, oh yes, they are definitely 2 points or they're definitely one. And so the criterion that has been used is somewhat arbitrary, but it is one that is used by microscopists generally. It's called the Rayleigh criterion. And maybe to get started here, let me just show you a pair of points that are moved closer and closer together, and we'll talk about why the Rayleigh criterion is a valuable way of looking at this. Rayleigh was a physicist who came up with this as an idea. There's nothing pure about it, but it is a very nice and straightforward way of thinking about resolution. So how close can 2 points sources be and their images still be seen as 2 points? So this isn't about how close they are in real space, it's how close in their image space they are, and still can we resolve them as separate objects. So here are a series of points, and if we start with the one up there, all the way here, no doubt those are 2 separate points. They're separated, there's a dark area between them. If we look all the way down here, where they're sitting on top of each other, then it would be very hard for anyone to say that they're 2 points, although this is probably much brighter than each of those points. And one might even use other kinds of information to infer that there may be more than 1 point of light on top of each other. But the Rayleigh criterion, which is somewhere in the middle of this range, is this one up here. There are other criteria known as the sparrow or the half-width, half-maximum, which are not used much in microscopy. So we'll just focus on the Rayleigh criterion because that's the one that turns out to be valuable. So there's no generally accepted criterion, but most microscopists use the Rayleigh criterion for their resolution limit, and partly because this distance between these 2 points is 0.61 lambda over NA. That is why that criterion is called the Rayleigh criterion. And so what it means, if you remember from previous discussions, the distance 0.61 lambda over NA is the distance from a point to the middle of the first dark ring. So if the second spot's peak intensity is sitting right on top of the dark ring of the first point, then they are at the Rayleigh criterion distance apart, which is 0.61 lambda over NA, and that is typically used as a resolution limit. Even though these points that are closer together you might still say are separate points, the Rayleigh criterion is 0.61 lambda over NA. If we look at the intensity profiles of these points with a line going through them, we can see that if we put them at 0.61 lambda over NA, the peak of each one is sitting at the first dark ring, the first dark area of the other, and where their intensities add right between, you drop the intensity by about 26% from the intensity at the first one. So that's the lateral resolution Rayleigh criterion. You could also have a XZ or YZ in depth Rayleigh criterion, which would now be 2n lambda over NA squared, based on something I told you in a previous discussion, and that is also a drop of around 20%, 19% between the two. So those would be the lateral over here and the depth over here Rayleigh criterion. The Rayleigh criterion gives you a hint that if objects are closer than that, they will be hard to resolve. And based on what we've discussed previously about the point spread function, you know as the numerical aperture goes up, 0.61 over NA goes down because NA is in the denominator. So it should be possible to resolve objects that would at the same distance apart be blurred with a low numerical aperture lens would be sharply in focus with a high numerical aperture lens. And this Following picture, I think, makes that point pretty clearly. So here's a bunch of beads imaged at the same magnification, mind you, but just with different numerical apertures. And you can see with a low numerical aperture lens, you just have this big blob. You probably infer that there's more than one thing in there, but you could have a hard time counting. With a medium NA, you begin to get the sense that there are individual objects, but the exact number would be hard to see. But with a high numerical aperture lens, now you see this remarkable set of beads. They have lots of rings around them, but you can discriminate each and every one of them. So the higher the NA, the smaller the Rayleigh criterion, and the better the resolution. An important point about this is, however, that if the beads are smaller than the resolution limit of light, the point spread function says that they're basically going to look the same. Even though they get smaller and smaller, the resolution limit limits how well you can resolve a small point. So if we look at a bead that's below the diffraction limit or the point spread function limit of a light microscope, which is, even the best objectives, it's not going to be much better than around 200 nanometers. So a 138 nanometer bead will be still a little fuzzier than 138 nanometers, even with a good oil objective like a 1.4 NA objective with 480 nanometer light. As we look at beads that are smaller, like 114 nanometers, and do the computation of the point spread function, there is a slight shrinkage of the size of the point spread function, but it's pretty subtle. And as we go to now 90 nanometers, there's still a little bit of shrinkage, but it's not much. And then you see as we go to 66, 42, and finally 18 nanometers, those images are all rather similar. So there is no ability, because of the diffraction limit, to get any better resolution than 0.61 lambda over NA. So image size does not change at all computationally once one's below about 60 nanometers. These objects will get dimmer because there's less light coming out, so you might be able to infer from a diffraction limited point that it must be a small object if it's very dim, and must be slightly bigger object if it's brighter, but in fact you can't infer it from the dimensions. So this is a fundamental limit of light microscopy based on diffraction. As you probably know, there are tools that kind of break through this limitation. They're not something I'm going to talk about today, but they are worth keeping in mind if one wants to get more resolution. What I would like to talk about is that if you have a resolution limit and you want to get the most out of that objective, you have to not only pay attention to the quality of the objective, but the image itself has to have a grain that's capable of seeing the finest details. And that often is an obvious missed point, an opportunity in a lot of imaging, where people have very expensive objectives, but they don't take images at sufficient resolution in the imaging plane to see all the details that actually exist there. So I want to talk a little bit about sampling an image and why one has to think about this a little more deeply than perhaps you might immediately think about. You might say, well, if the resolution limit is 0.61 lambda over NA, I should just have a resolution in my image plane of 0.61 lambda over NA. That should be the distance between the pixels in the magnified image. And you'll see that that is way insufficient. So let's start with an image. And here it is of something. And I would say most of you would probably say, I don't know what that is. It's something, but it's hard to tell what it is. And you would say the reason you can't tell is that there's not enough resolution in the image to tell. In fact, it is a blurry image. It's not been blurred. It's just that it's been sampled with pixels that are way too big to see the details. So let's move up by sampling with a higher grain in our imaging plane. Same camera, same image, but now we're using better paper that has a finer resolution. And now you probably would say, oh, that's probably a zebra. But it doesn't look like a pretty good zebra. I mean, you know where the head is, but the details seem to be a little funny. And if we move up a little further, you now say, oh yeah, this is a zebra, but it has some unusual features. And one of the features I like to point out is this checkerboard of stripes here running in two different directions. And you may know enough about zebras to know that zebras don't have checkerboards. They really are striped. And yet this image has this artifact of stripes running in two different directions. This is known as aliasing, and it is a very obvious and problematic aspect of images because, especially as a researcher, you're looking at things that may have not been looked at before. So if you see objects with some periodicity, you may say, oh, that really is there, because you don't know it's a zebra. You don't know what it is. But it is an artifact of sampling. So let's sample the same image at higher resolution. And you see, as I go back and forth here, that those checkerboards have now turned into vertical stripes. Well, not vertical, but diagonal stripes. You may also notice on the on the nose, I think this is the nose of a zebra. I don't know what you call that part of a zebra, but headed towards the nostrils, there are a couple of stripes that are running diagonally. Is that real? Do zebras have stripes like that? Well, let's resolve this image by using even better paper or a better camera with higher, not better lens, just a better resolution, more megapixels, let's say if it's a CCD or a solid state camera. And you see that those stripes have also disappeared now. So now, do we have the real zebra yet? Well, it's hard to know. You may notice on the other side of the nose, there are still some horizontal, some diagonal lines that seem not symmetric with the other side. Well, let's image at even higher resolution, and you see those have gone away. So this looks like a pretty good image of a zebra. There is still, I'm not sure you're going to be able to see on your monitors, there are still some bands that are running horizontal across the front of the nose at the finest resolution. If we go one higher, and for most of you, you probably won't even detect the difference, now finally even the vertical stripes there are obvious, whereas in this previous image, they're slightly diagonal. So aliasing, this kind of problem of lower resolution, is not just that things are fuzzy, but it generates areas of light and areas of dark that are artifacts. And this can severely crimp your ability to interpret an image. So that's why I'm spending so much time with this. So how do you know how much resolution you need? The person who has helped us best with this is a guy named Harry Nyquist. And some of you may have heard of the Nyquist Limit. It's a law that was named after him in 1933. He was a scientist interested in sound, and he stated that sound must be sampled at least twice the highest frequency in order to extract all the information from the bandwidth and accurately represent the original acoustic energy. So his idea was, for example, if the human ear can hear frequencies up to 20,000 hertz, 20 kilohertz, then if you want to hear those frequencies without artifacts, you're going to have to sample that sound at least twice that frequency. And so a modern CD that is a high fidelity recording is at 44 kilohertz. Not because you can hear 44 kilohertz, but in order to hear 20 kilohertz accurately, you have to be sampling twice the highest frequency. Phone lines pass frequencies up to 4 kilohertz, so the phone company samples sounds at 8 kilohertz. So this is true in sound, but it's also true in all forms of signals that have oscillations, that you need to sample twice the highest frequency you're interested in. So the sampling theorem, based on Nyquist, is a continuous function can be completely represented by a set of equally spaced samples if the samples occur at more than twice the frequency of the highest frequency component of the function. Now with our imaging, the highest frequency component is 0.61 lambda over NA. So if you want to see 0.61 lambda over NA details, you're going to have to sample that kind of oscillation with at least 2 points between each point. So to capture a function with maximum frequency, the sample has to be sampled at twice that frequency. This is called the Nyquist limit. And the reason aliasing occurs is shown in this bottom diagram. So if you have a sinusoid, let's say zebra stripes that are bright and dark, that's that red line. So it's an oscillation between bright and dark, but you're only sampling once per wavelength here, so you only get one sample for every peak and trough. You're going to end up with a sinusoid, in this case, that's got half it goes from light to dark, but it has half the actual frequency of the original data. And the aliasing generates these kind of nice patterns that are just total artifacts of subsampling the data. So in the case of the resolution limit of light, which is 0.61 lambda over Na, there are those two spots. They're separated by 0.61 lambda over Na. If you want to resolve them, you're going to have 2 pixels between them. So the Nyquist limit is 0.3 lambda over Na. That is, your imaging plane is going to have to be able to see something half as big as the limit of resolution. For example, if you're imaging and putting your image onto a charge-coupled device, in the spec sheet for the charge-coupled device, it is a datum which tells you the size of the pixels on the charge-coupled device. So a charge-coupled device might have pixels that are 12 by 12 microns, square pixels, and you can figure out what the size of your image will be in your microscope. So for example, if you're using a 1.4 numerical aperture lens at 480 nanometers, the resolution limit, 0.61 lambda over Na, is 0.22 microns. The 60x magnification is going to blow that 0.22 microns up into a bigger object. That is, it's going to go 0.22 times 60. So now your diffraction limited size is 13.2 microns, which is the distance of the resolution image on the faceplate. Your pixels on your faceplate are 12 microns apart. So this is matching very well the resolution limit, but that's not enough to see the finest details. As I said, you have to oversample by a factor of 2. So what do? Well, you're using a 60x lens that's 1.4 numerical aperture. You've got to get more magnification. One of the reasons companies sell 100x 1.4 Na lenses is not because they have better resolving power than 60x, but they add that empty extra magnification that then allows you to better match the size of the image with the resolution of the CCD. Another thing is some people have mag changers, they're called optivars, right in the microscope that blow up the image, just add magnification, and so those are the kinds of things you can do. So here dramatically, a mag changer to zoom by 2x or use a 100x objective. Then the resolution limit is now 26.4 microns on the CCD if you do a mag change of 2, which is greater than twice the sampling resolution of 12 microns. So now you will get the full value of that high numerical aperture lens. But if you need more resolution, what are the things you can do? So I'll just review some that we've already talked about. One is you can go from red light to blue light or ultraviolet light to get higher resolution, because 0.61 lambda over Na, as the lambda gets smaller, the wavelength gets smaller, the resolution of the point spread function gets tighter and you get better resolution. A second thing is if you're doing your work in air, you can go to water. And if you're doing it in water, you can go to glycerin. If you're doing it in glycerin, you can go to oil. Each of those increases the numerical aperture, because the numerical aperture is n, the index of refraction, times the angle, half angle of acceptance. So higher index immersion fluid will give you better resolution. Of course, you've got to use an objective that takes those different immersion fluids. As I've already mentioned, the confocal, if you stop that pinhole down to the size of an airy disk or smaller, you get an increase of about the square root of 2, 0.4. Improvement in resolution, so that always can be used. If you are studying just single spots of light, single molecules, in fact, then you can know their position in space to much greater resolution, because the center of the spot is a very accurate rendering of where that object is. So people who track the movement of objects can go well beyond the diffraction limit, because the movement of the object from one place to another can be tracked by looking at the center of that spot. Indeed, some of the super resolution techniques take advantage of just that property to give you super resolution. And some of you may know that there's this whole set of other techniques available called super resolution. Before mentioning those, I'll also tell you that if you have two different colored objects, they can become much closer together because they're not interfering with each other. They're different colors, so they're disambiguated, so one can get the distance from one object to another that's much closer than the diffraction limit. So for example, in a synapse, the presynaptic terminal can be labeled with one color and the postsynaptic with another color, and you can see distances apart that are well below the diffraction limit by virtue of different colors. But that last thing is super resolution, nanoscopy, and I think there'll be other discussions of this in other lectures. Thank you.